Hi, my name is Matthias Brenner, and I'm a doctoral candidate at the Chair for Construction Heritage and Preservation at ETH Zurich. In the current research project, we're investigating the potential of digital fabrication for repair in architecture. Hereby, the focus lies on the building stock of the 1970s to 90s, since these buildings, after roughly 40 years, now require attention regarding their maintenance and repair. During this period, simultaneously with the prevalence of postmodernism, another style emerged. For its expressive designs, the use of new technologies and materials can be observed, particularly around innovative facade and supporting structures. These constructions are commonly referred to as high-tech architecture. Peter Buchanan associated this term in 1983 with buildings whose design concept is based on the use and display of advanced technology. A compilation of features, building on the ones of Davies, Buchanan, and Brenner, may trace different high-tech design approaches from Britain to France, Germany, and Switzerland. First, of course, the structure and building services are situated outside the protective building envelope. Both are emphasized and sometimes even codified through coating and signal colors. Oftentimes, industrial, semi-finished products are showcased and carefully joined with custom-made components. This leads to complex node geometries, which are almost celebrated in many cases. New material capabilities and related innovations in manufacturing lead to innovative building envelopes, inspired by transportation design and the concept of a vehicle body. Other facade designs feature intricate technological details, evoking an almost machine-like aesthetic. Generally, an underlying claim of technical superiority can be observed when investigating these objects. Obviously, one of the most famous buildings of this movement is the Centre Pompidou in Paris, designed by Renzo Piano and Richard Rogers and inaugurated in 1977. But already after 20 years, the iconic art museum had to be closed in 1997 for several years due to its need for renovation and repair. The story repeats itself roughly 25 years later, since the museum is now planned to close again for repair works. This illustrates that especially the innovative structures of the 1970s to 90s are now in dire need of careful repair interventions. Ecomos states that constructions of the second half of the 20th century pose challenges for their conservation due to, I quote, new and experimentally used materials or construction methods and the lack of specific professional experience with their repair, end quote. The International Council on Monuments and Sites focuses in Article 3 of the 2011 Madrid document on the technical characteristics of the architectural heritage of this period. It stresses the need for specific repair methods for more recent building materials and construction techniques. These buildings, considered and remaining technically sophisticated, start to be due for innovations in the areas of facade and building services. Here, a collaboration between civil as well as mechanical engineers, architects, and preservation specialists is essential from our point of view, so that investigations don't only consider the distinct design features, but also its constructive aspects. As part of our ongoing research into these two high-tech buildings in Switzerland, the CLA building of ETH Zurich on the left and the distribution center of the Swiss Post in Müllingen on the right, I'd like to go into more detail on the case study of the CLA. In the event of a repair scenario of the facade of the structure, one challenge becomes quite apparent. The methods of monument preservation as well as manual repairs seem to be only partially suitable for dealing with this building stock. The objects, which were highly technical at the time of their construction, seem to call for an expansion of our repertoire of tools for their repair. The manual repair or the manual reproduction of industrially manufactured components would be possible in principle, but would not be process conform and therefore contradict the object's basic principle. In addition, according to the Ecomos document, it seems appropriate not to resort to manual repair measures when preserving these buildings. It rather encourages one to instead use the latest technologies in accordance with the fundamental concept of these objects. Here, recent advances in digital fabrication offer viable solutions. If implemented successfully, this has the potential to reduce the exchange and replacement of components in the event of damage, and at the same time to produce components with less waste and thus with more resource efficiency. In particular, the innovative constructions of the 1980s represent promising case studies for investigating the potential of digital fabrication as a repair tool. In order to carry out a repair intervention of this nature, it is essential to have an accurate 3D model of the actual geometry of the building component. Typically, digital plans are not available, and in many cases, the original construction documents have been lost or lack sufficient detail for a digital reproduction. Furthermore, the companies that originally manufactured these parts have either ceased to exist or no longer produce them. As a result, the building components found on site serve as the primary source for the reverse engineering process of its spare parts. Archival research supplements this documentation process. Utilizing surveying techniques like photogrammetry, structure for motion, laser scanning, precise construction models can be generated. By subsequently combining reverse engineering with digital fabrication technologies, innovative repair strategies can be realized. Using the example of the CLA building, it's the goal to illustrate the complete workflow necessary for the repair of non-planar bespoke metal components. The CLA building is part of the central campus of ETH Zurich. It was built in 2 stages between 1986 and 1998 by Fosco Oppenheim Vogt architects. Appropriately, one could argue that chairs for process engineering, robotics, and mechanical engineering are situated in this high-tech building. The facade of the longitudinal building is divided into 2 parts. On the southwest side, a multi-part filigree technical facade was constructed, while the facade on the north side, which appears more closed, consists of anthracite-colored horizontal metal slats. This division of the building is not only visible on the outside, but can also be read internally. A central corridor with doors on both sides divides the building lengthwise. In the southwest, offices are located with big openings, allowing for lots of daylight and views over the city. In the northeast, laboratories are placed with limited openings to optimize for cooling. A filigree brise-soleil structure was installed on the southern facade to reduce the cooling load. The mock-up of the facade construction shows the expressive sun protection elements of the southwest facade, which is made of 2 layers of laminated safety glass, between which there's a white PVB film. These flat elements are anchored by thermal lacquered steel saddles and vertical support tubes made of stainless steel. These tailor-made special components are colored in green and red in this sketch of the architects. They were exclusively manufactured for this particular facade construction, but were mounted in small series repetitively over the whole southern facade section. From recently conducted interviews, we know how important it was to the architects that the components are joined as reversibly as possible, meaning they're screwed, slotted, and plugged. Following a repair scenario where one of the green metal joints of the shading construction was defective, a spare part as a targeted replacement would help to keep the overall facade structure in place. Since, like many of the original construction companies, the metal facade company Soda no longer exists. Detailed construction drawings and plans are oftentimes lost. The ones that resurface after archival research are mostly 2-dimensional drawings that are not detailed enough to form a basis for the production of a non-planar spare part requiring a 3-dimensional geometry. Therefore, new construction drawings based on a 3D model need to be produced starting from the object on site. Here, building surveying techniques offer promising results. The photogrammetry of a facade component could theoretically be done by employing a drone, if in that case there wasn't a no-fly zone in the center of Zurich because of the nearby helipad of the university hospital. But yes, in this case, also a bit of scaffolding and climbing gear do the trick. Once several hundred photos are taken on site, they can be fed into a photogrammetry software to calculate a detailed point cloud of the object. The first output is a sparse point cloud, here to be seen on the left, which then can be cleaned up by deleting unwanted points before it's recalculated in detail to produce a dense point cloud. This dense model can then be converted both to a wireframe geometry and a solid geometry with texture. To assess the accuracy and level of precision of the calculated model, a point cloud confidence model can be helpful. here on the right, ranging from green to red. In the end, this method allows for the reverse engineering of a highly precise 3D model as a replacement for the missing original detailed construction drawings. Based on the 3D model, a first prototype at the scale of 1:1 was produced using nylon 3D printing. This was done to assess the quality of the mesh model that was directly exported from the point cloud. At a closer look, certain inaccuracies and surface imperfections become visible. This occurs because of the inherent material properties of the scanned shiny metal components. Sunlight reflections of metal objects pose a huge challenge for the photogrammetry process. To increase the quality of the final 3D printed demonstrator out of metal, an additional step was added to the workflow. Here, the point cloud serves as a three-dimensional intermediary to the model that consists of simple and optimized shapes. What that means in terms of process is that the point cloud model was filleted with several section planes. Here in this image, you can spot them marked in red and blue. A more precise overall geometric model was then constructed by interpolating the section curves. The outcome of this reverse engineering process is a 3D model with a smooth but also precise surface by approximating its non-planar envelope geometry. The same process was used to create the 3D models of the neighboring elements. The connection between these two joints is missing in this image since it's a conventional metal rod with a chrome coating, which will of course not be 3D printed, but just cut to length and mounted together with the 3D printed components. Besides the 3D model, the outcome of the reverse engineering process is also a set of construction drawings that now supplement the hand sketch of the architects. In the last step, the 3D model is the basis for the digital fabrication process. Metal additive manufacturing technologies like DED or WAM depose metal substances exactly where needed, layer by layer, to additively produce a component. Currently, the robotic welding process using WAM technology is being applied in collaboration with the Advanced Manufacturing Lab at ETH Zurich. Wire arc additive manufacturing, WAM, is a manufacturing process for 3D printing or repairing metal parts. It belongs to the direct energy deposition, in short DED family, of additive manufacturing processes. The WAM process involves welding layers of metal until the desired 3D shape is created. A welding robot with an integrated power source and wire feeder is used to manufacture components with WAM. A welding torch attached to the robot is used to melt the wire precisely where needed. The object being produced in this video is not part of the facade of the CLA building, but should merely illustrate the fabrication process using WAM technology. As a little outlook, I'd like to shortly introduce another case study of our ongoing research, the Briefzentrum Zürich-Müllingen. The huge structure right at the city boundary of Zurich was built between 1978 and 85 and was designed by Theo Hotz architects in Zurich. With its enormous size of approximately 250 by 140 meters, it contrasts the small-scale solitary plot structure of the residential zone surrounding it. Its volume is articulated in two main building parts. One 26-meter high operation facility which mainly houses the sorting and distribution machinery, and a 48-meter high service tower. In the repair case of this facade, an aluminum sheet as a spare part needs to be modeled and subsequently fabricated. First, a building survey was conducted utilizing drone-based photogrammetry in combination with terrestrial laser scanning, which allows for an accurate modeling of the high facade structure. At its core, the project focuses on another fabrication method. It shows that not just additive, but also formative manufacturing techniques can be helpful to produce a spare part for a facade. Here, robotic incremental sheet forming is used to produce spare parts in the form of custom bent aluminum sheets. Overall, I hope to have illustrated how we can use high-tech capabilities of our time to rather repair than demolish the innovative facades of the second half of the 20th century. This would significantly reduce both the financial and environmental impacts of such interventions. It would also prolong the lifespan of building parts, while simultaneously reducing construction-related waste. This approach would transform the way construction industry deals with complex facade elements in need of maintenance and repair, and open the door for more circular business models. Finally, I'd like to shortly mention 2 upcoming events which underline the importance and show the current interest in this topic. Arch Plus is hosting a big exhibition on the topic of repair in Berlin this fall, showcasing, among other things, the CLA facade and its associated repair process. And in September, we'll host an international conference on the topic of high-tech heritage and permanence of innovation here at ETH Zurich. Thank you very much.